So electron affinity. Bree, can you remind me of what that meant? Awesome. So energy change associated with gaining an electron this time. So again, ionization energy is losing an electron, electron affinity is gaining an electron. If you notice, we might even compare these. Losing an electron is kind of like oxidation. Gaining an electron is kind of like reduction, back from chapter 4. So we can associate these with oxidation and reduction as well, but gaining an electron. And if we look, we said the general trend here increases going to the right, all the way to the halogens. But the noble gases aren't part of this trend. So it stops at the group 7, halogens. Noble gases, not part of this trend. So in this case, we said the energy change here is typically negative. It's exothermic. If it costs energy to remove one, then it's going to release energy if you gain one. That's where the electron wants to go. And so when we say this increase is going to the right, again, we mean that means it gets more and more negative. It releases more and more energy. But again, we got some exceptions here. Noble gases, not part of this trend. Why don't the noble gases want to gain an electron? Yeah, they're stable. They're good. They don't want to lose one. They also don't want to gain one. So that makes sense. Instead of having a negative electron affinity, the noble gases, they're all positive. Like you think you're going to make chlorine's day because you give an electron. And you know what? You will. Chlorine has the most negative electron affinity. You give him an electron, he's so happy, he just starts releasing energy, showering the world with excess energy. And you're like, dude, I just made chlorine's day. Let me go give argon an electron. And you give argon an electron, and he punches you in the face. He's not happy about it. He does not want an electron. But the noble gases are not the only one. Who else, not just filled octets, they didn't want to lose one. They also don't want to gain one. Who else, which columns, don't want to gain electrons either? Shells that are half full, like nitrogen's column on the periodic table. He, again, half full. He doesn't want to lose one. He also doesn't want to gain one. And so we find out that it's not just the noble gases. So it's not just the noble gases, but it's nitrogen's column over here as well. If I can write this. You got nitrogen and phosphorus and so on and so forth down there. But who else doesn't want to lose any electrons? As well as gain electrons, I should say. Whose column? Not boron. Notice boron's like, dude, if you want to take one away from me, it's not so bad. But it's beryllium's column. He didn't want to lose any, he's good. He also doesn't want to gain any because he's good. And so in this case, it's, beryllium and magnesium and so on and so forth down there. These guys are the exceptions once again. So they were exceptions on ionization energy, or at least part of the exceptions of the trend. They're also the exceptions for electron affinity. Rather than being, again, more and more negative, most of these are actually positive electron affinities. They don't want to gain one.
So would that be the whole row?
It'd be the entire row. And again, they might not all be positive, but a lot of them are at least really close to zero. They're not very negative for the couple that are still negative. But they're definitely exceptions in the trend. Cool, if you notice, there's also no vertical trend here. I give you a horizontal trend, it gets more negative going to the right, but there's no vertical trend. And the reason there's no vertical trend is because the vertical trend it gets more negative going towards period 3 with chlorine's period. So it gets more negative going towards chlorine there, but also going down towards chlorine there. So there's no well-defined single vertical trend. The third row, it turns out, for whatever reason, is the most negative. And so we usually don't even tell you that. We just usually just say, just remember that it's going left to right towards the halogens, and remember the exceptions. Now, electronegativity, another trend. And again here, this is technically something you're going to see in the next chapter, but I'm going to group it with this chapter since we're covering a bunch of trends. Let's cover this one too. And again, who's the most electronegative element on the periodic table? Not francium, he's the biggest, but fluorine, there you go. And so fluorine up towards the upper right-hand corner, and electronegativity increases going towards fluorine. And again, that means it increases going to the right towards fluorine and going up towards fluorine. But again, you should know not only who's first, and it definitely is fluorine, but who's second place? Oxygen is second place. And the reason I tell you that is, again, because oxygen beats out chlorine. They're both right next to fluorine in this case, but oxygen, you should know, is also second place. So in this case, what this could allow you to determine is what we call the polarity of a bond. So if I had, say, a CF bond, an NF bond, and an OF bond. What this electronegativity allows us to determine is when we have a covalent bond now and sharing of electrons going on, the electrons aren't always shared evenly. And in this case, whoever's more electronegative is pulling those shared electrons closer to him. And so carbon and fluorine here, if you notice, if we kind of fill in some spaces here, we had fluorine, oxygen, nitrogen, carbon, boron in that column, right? So fluorine's more electronegative than carbon. And so in this bond here, fluorine's pulling electrons towards himself. Sometimes we represent that with an arrow. Again, we'll see this again in the next chapter. And what this means is that because those electrons are closer to fluorine, that means fluorine has a little bit extra electrons. And as a result, fluorine's just a little bit negative. That's the Greek letter lowercase d, delta. So it means partial negative. And because carbon now, having the electrons pulled away from him, doesn't have his fair share, and so he's just a little bit partially positive. And we now refer to that bond as being a polar bond. It has a positive pole and a negative pole. We call it a dipole in this case, or a dipole moment. In this case, though, which of these bonds has the most significant inequality in how those electrons are shared? And what that means is then the most negative on one side, the most positive on the other. Yeah. In this case, the bigger the difference in electronegativity, then the bigger the difference in polarity here. In this case, or say the more polar bond. And so in this case, because there's a bigger difference between carbon and fluorine, than between nitrogen and fluorine, than between oxygen and fluorine, a bigger difference in electronegativity, this is the most polar of these three bonds. And so that might be something we have to rank a little bit later on. We'll talk about this again later in the night. So that's your trend in electronegativity. Couple other things about this chapter. You get a lot of descriptive chemistry in this chapter. I'm not going to talk about much of it because most of it's like memorize this, memorize this. However, there's a couple things I want to talk about. One, if I told you that are some elements that are really reactive with water, what elements are most likely to be really reactive with water? More specific. Which group of metals? Yeah, group 1 metals, the alkali metals. They're really reactive with water. And the key is when a metal reacts with water, if it reacts with water, it's doing a redox reaction and it's going to lose electrons. Well, losing electrons, how much energy does it take to lose electrons? What kind of energy is that? Ionization energy. So it's ionization energy. And so in this case, who loses electrons the easiest? Who has the lowest ionization energies? The alkali metals. And that's why the alkali metals are so reactive with water, because they're willing to lose electrons the easiest when they react with water. So you should know the alkali metals, most reactive with water. And you should know that the larger ones are the more reactive ones because they have even lower ionization energies. Cool. The other thing I want to talk about from that chapter is talking about metal oxides versus non-metal oxides. What do you suppose has to be true about an oxide's chemical formula for it to be considered an oxide? Has to have what element? Oxygen, sweet. So notice like a metal oxide might be like sodium oxide, or maybe, potassium oxide, or maybe barium oxide. They're all metals with oxygen. A non-metal oxide, on the other hand, might be like carbon dioxide, or like sulfur trioxide, or maybe nitrogen dioxide, all non-metal oxides. Cool, and there's a big property about these two different types of oxides that you should know. Now let me ask you a question. Do you recognize any of these as being pollution gases? Anything up here as pollution gases? Yeah, carbon dioxide, biggest pollution gas, right? Your big greenhouse gas. But these also come off your tailpipe as well. These are less of these in the atmosphere, but these are also pollution gases. These are all pollution gases. And when they mix with the water in the air, and then that water comes down as rain, we call that rain acid rain. And the key is this: non-metal oxides are acidic, all of them. And we contrast that because metal oxides, on the other hand, are, guess what? Basic. And that's something you should take away. You may get a question on the test that lists a whole bunch of oxides, and it says which one of these is acidic, or which one of these is basic. And you just have to pick the one from the correct category. Just knowing that metal oxides are bases, they make the pH in a solution go higher, whereas non-metal oxides are acids, they make the pH in a solution go lower.